Hi, welcome back to Maths with Armien. This is part 4 of differential calculus, and we're going to look at interpretations of graphs of cubic functions and specifically some inequality relationships. In this lesson, we're going to first of all look at finding equation of cubic functions where the graphs are given. Then we're going to show you how we can interpret graphs of cubic functions and specifically some inequality relationships. And then we're going to do some problems with detailed solutions, and as usual there will be an exercise worksheet for you to practice these concepts and skills. Let's start with finding equations of some cubic. We're going to start off with finding equations of cubic functions where the roots are given. Being a cubic, what's the maximum number of roots? That's right, 3. So let's say we have there the 3 roots, R1, R2 and R3. Let's look at it graphically. There we have a cubic function, there we have R1, and you can see there's R2 and there's R3. Okay, being a cubic function, this is the standard form of a cubic function, consists of 4 terms. I have A3, B2, C and D. Now because I have a coefficient of A, I can have A, then x minus the 1 root, x minus the 2nd root, x minus the 3rd root. Okay, let's look at an example. Here we have an example, and let's see what is given. We have a root at -1, we have a root at 4, and we have a root at 7. So we can actually substitute these roots directly now. So if I substitute those roots, the first one, -1 becomes +1, +4 becomes -4, and +7 becomes -7. But if we look there, there's another point that's given, the y-intercept 0 and 28. Now if we substitute 0 and 28, x is equal to 0, and what will be 28? That's right, the fx. So if I substitute the 0, and fx now is 28. And if we calculate that, that's -4 times -7 is 28. 28a equal to 28. It's very simple. A is equal to 1. Now, I now substitute a as a 1. And I'm going back to my fx now. So a is a 1, I'll have x plus 1. To expand that, it's advisable to expand by taking the last 2 brackets first. Expand them, and then I end up with x squared -11x and plus 28. And then you can expand that further. Maybe you can do it in an additional step. And the final part there would be x cubed minus 10x squared plus 17x plus 28. And there we found the equation here. Let's look at the following situation here, where the roots are given, but in this case, only 2 roots are given. And one of the roots is a turning point. There's the one root R1, and there's the other root R2. Now notice R2 here is a turning point. That means that these we have equal roots at that particular point there. So that's the form of the cubic equation. Let's insert the first root, x minus R1, x minus R2. As you can see, the R2 is the one that's going to be repeated. Let's look at an example. What is the first root? -3. And the repeated one? 2. See, the repeated one is the one that is associated with either a local maximum or a local minimum. There's the y-intercept. So let's substitute the 2 given roots. So that's going to be x plus 3. The other one is x minus 2. And it's the x minus 2 that is going to be repeated. Now we have to find the value of a. That we can do by substituting the other points, 0 and -12. Substitute that. We end up here with, that gives us 12a equal to -12. So a is -1. Now we can substitute the -1 back into that expression, and we multiply these 2 factors, the second 2 factors there, and we expand that. We end up with x squared minus 4x plus 4, and if we remove all of that, here we end up with negative x cubed plus x squared plus 8x minus 12. Let's look at the following situation where only one real root is given. There we have it graphically. What is the real root? R1. Now we're going to consider the cubic equation in this form. What is the one root? R1. So we have x minus R1, and the other factor of the cubic here would be a quadratic, which has non-real root, x squared plus mx plus p. Let's take an example. What is the real root here? X equal to 3. So let's substitute that one root. There's a positive 3, so I end up with x minus 3. Then we have a quadratic, and there is a quadratic x squared plus mx plus p. Because we have two unknowns m and p, I need 2 points. And what are the 2 points? Let's look for them. 0 and negative 33, and negative 2 and negative 25. Which one will be the easy one to substitute? That's correct, the 0 and the negative 33. So let's substitute that. There I've inserted 0, and there's my negative 33. This gives me negative 3p equal to negative 33, which leads us to p equal to 11. Now we're going to substitute the negative 2 and the negative 25. There we substitute the negative 2, negative 2, negative 2, and remember this is a 11. So I end up here with negative 5p equal to negative 25, which leaves us with m equal to 5. Now I can expand. I now know what the m and the p is. So I insert the m value and the p value, and I just expand that, and I end up with a cubic expression, x cubed plus 2x squared minus 4x minus 33. Now let's look at examples here where there are no roots given. We have 3 points. Let's say you look at an example there we have 3 points. So we have a turning point in this case, and a y-intercept, and another turning. So we've got 3 sets of points there. But no roots. See, there are no roots. There is a point, and we also have a y-intercept. Let's look at this. There's a p and a q and a r, so there are 3 unknowns. So if there's 3 unknowns, we should have 1, 2, 3, right? 3 would be sufficient to be able to, we need 3. So again there we start with the easier one, which is 0 and 16. Substitute 0 and 16. So the r becomes a 16. So r is already equal to 16. Now we need to find the p and the q. To do that, we substitute 1 and 23 and negative 2 and negative 4. Maybe it's easier to start with a positive. Let's substitute the positive value in first, and then we end up with a linear p plus q equal to 10. Now let's take the negative. Just be more careful with the negative. Negative 2 cubed is negative 8. That's going to be 4 times negative 3, which is 12. That's negative 2 cubed plus 16. And if we simplify that, we end up with 4p plus q. So now we have to solve simultaneously. Now remember, you can either do it by elimination or substitution or use your calculator. Whichever method you used, the correct value then would be p equal to negative 2 and q equal to 12. Then we substitute the p and we substitute the q, and we've already worked out the 16. And there's my cubic equation. Example. This one is slightly different. We don't have 2 turning points but 1 turning point. How do we find the cubic equation if we only have 1 turning point? Let's see what we have there. There we have the form of the equation. How many missing values there? A, B, and C. So that means I need 3 points. But I look there's no other point. You know, it's nothing hidden there. There's a 2 and a 1 and a 9. But this is a turning point. I will come back to that turning point. Again, start with the easier point. It will be 0 and 2. That will give you a C. Now we have two unknowns. So let's substitute the x and the y. In this case, 1 and 9. We substitute that. We end up with a plus b equal to 10. Now we already substituted 1 and 9 and 0 and 2. There's no other point. What do we do now? But let's see. They mentioned that 1, 9 is a turning point. What do we know about turning points? That's correct. The first derivative is equal to 0. So here we're going to use calculus to assist us further. So we find the first derivative equated to 0 and x equal to 1 where the first derivative is 0. So differentiate that, gives us 3ax squared minus 6x plus b equal to 0. Substitute 1. 1 squared is 1, so that becomes 3a negative 6 plus b, and we can simplify that, and that leaves us with 3a plus b equal to 6. Again, two unknowns, so I need two equations. Solve them simultaneously. Whichever technique. What are the techniques again? Either substitution or elimination, or just use your calculator. A equal to negative 2 and b equal to 12 are the two values, and once you have the values you can write down the equation there. Now next we're going to look at interpretation of graphs of cubic functions, and specifically some inequality relationships we're going to look at. Okay, let's look at where a curve increases or decreases. Let's look at a cubic function. There we've got a cubic function, and what does this point represent here? That's right, the local maximum, and this one local minimum. And at the local minimum I have a value a associated with it, which is the x coordinate. What do we refer to the a and the c here? That's correct, the critical values, right? Critical values are the x coordinates of the local maximum and the local minimum. Now if I want to find out where the curve increases or decreases, always start from the left side. Follow it here. What is happening here? It is increasing, and from there it decreases until it reaches the minimum, and then it increases. So the critical values will assist you in determining where a curve increases or decreases. So it increases from this side up to the A, then it decreases again up to the C, and then it increases again. So let's do that. Increasing, where is it increasing? From negative infinity to A. And increasing means, there is the first derivative greater than 0, or the gradient is greater than 0, or the m value is greater than 0. So there it's from negative infinity to A, and then this one is from C to infinity. It's advisable to write it rather in interval notation. It's much simpler to write the intervals in intervals where it increases and decreases, preferably in interval notation there. Decreasing. Where did we say it was decreasing? Let's see, where is it decreasing? It decreases if the gradient is less than 0. And if you now look at the decreasing portion, there's the decreasing, the one in green. I've color coded the increasing and decreasing. Decreasing is in green, and it decreases from A to C between the two critical values. Right. So if we want to determine intervals for increasing and decreasing, we use the turning points. Right? We determine the critical values using the turning. Now this is another concept we're going to refer to, and this is the concept of concavity. Let's look at our cubic function. There we've got a cubic function, and this point here, remember when we sketched curve, what was this one? That's right, this is the local maximum, and this one is the local minimum. But what is this one here? This is the inflection point. You still remember? There the tangent was above the curve, and at the inflection the tangent will then be below the curve there again in this situation. And here we have a critical value associated with that inflection, and that's the x coordinate of the critical value. How do we determine critical value of inflection? That's correct. We find the second derivative. So let's just look at this graph now. So if I look on the left side of my inflection point, this part of the curve, right? Can you see there's the inflection, and I go to the turning and I turn and it just goes down, 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 right? This type of curvature is known as concave. It concaves down, and actually the arrow can help you also to determine that. See there, it goes down that way. That's concave down. So on the left of the inflection point, and on the left there would be, what will the interval be? That's correct, from negative infinity to e. So it's a second derivative must be negative. Then x will be between negative infinity and the critical value of the inflection point there, right? Let's look at the other one. Now you can even see there, it's from the inflection, it turned and it went up. So this type of curvature here is known as concave. I'll let the arrow sort of assist you in determine the type of concavity. And you can see it's from the inflection point on the right side of the inflection point. So that is concave up, and it's concave up when the second derivative is greater than 0. In this case, it's from on the right side of the inflection point. That is from e to infinity. Right? And you just look at the two graphs there. You can see the concave up, concave down is the one in green, and concave up is the one. And from the inflection, you can see it goes up that way. And the inflection point is where the concavity changes. It changes from up to down. Now we want to compare the different curves, right? The function, its first derivative and its second derivative. Let's say there's the curve there, so that's the f, that's the one in yellow. We're going to compare that. And if I look at this curve here, this one has a x-intercept and an x-intercept and an x-intercept, right? And there we have the local maximum and the local minimum, and there we have the inflection point. And now you can see these faint dotted lines there. It's just to help us with the intervals. You can see there it's from negative infinity to that point, then from this point up to this one, then from there up to that critical value, from there to the intercept, then to a critical value, then to an intercept, and then to infinity there. Okay, so the cubic function is the one there in yellow. When we have the first derivative of a cubic function is a function like this, and which shape? You still recall this shape? That's correct, it's a quadratic, right? So if you have a cubic function, its first derivative is a quadratic, and there's the quadratic there. And this quadratic, if you look at it carefully, that critical value for its local maximum, it becomes the x-intercept there, right? And the critical value for the minimum becomes the x-intercept of the first derivative. And if you find the second derivative, the second derivative of a cubic is that's right, it's a linear function. Okay, so this is important for you to know. A cubic function, its first derivative is quadratic, and its second derivative is a linear function there. Let's just do them individually. There's the cubic function. Okay, just a little bit different there. So I have a cubic function here, and what are the x-intercepts here? There, the x-intercept is at the point K. It's a bit small there. There's the x-intercept at point K. That only has one x-intercept. Let's look at that same one, and let's look at the quadratic function for that. The quadratic is the first derivative. There's it there, right? And you can see the critical value A will match with that x-intercept there. The critical value C for the minimum there. So there I have the critical values are actually the x-intercepts of the first derivative. And the second derivative is a linear function, and there we have the linear function, right? and this x-intercept corresponds actually with the turning point of the quadratic. And that critical value here, that's actually the critical value associated with the inflection point. Now let's look at some inequalities now. The inequality interval for, what does this mean? This means the first derivative less than 0. What does first derivative also mean? The gradient is less than 0. If the gradient is less than 0, what does that mean? That's correct. It means the graph is decreasing, right? So if I have a first derivative, I look at the critical values, and the critical values we obtain from the turning points. So what's there? The critical values are A and C. So that means where's the graph? Decreasing. Can you see where the graph is decreasing? Let's follow there. There the graph is increasing and then it decreases. So where does it decrease? That's correct, between the two critical values. So it decreases there. I have to look at the turning point, which gives, and then it decreases between A and C. Let's also look at the second. You see there, this is the original function f, and this is its derivative. Remember, this is cubic and this becomes quadratic. So the x-intercepts correspond with the critical values associated with the local maximum and local minimum. So the x-intercepts here are actually the same as the critical values for the local maximum and local minimum. So if we have the first derivative less, so I just look at the first derivative graph, not that one. So where is the first derivative less than 0? You can see this dotted, there's the less than portion. The solid one is the greater part. So where is it less than? Between, that's correct, between A and C. Okay, so in this case, I look at the graph and I look at the portion that is below the x-axis. Okay, so there I use the x-intercepts and it lies between them from A to C. And you see it's exactly the same answer. So if I can find the first derivative less than 0 by looking at the original graph, but then I have to look at the critical values there. But if I have the graph of the first derivative, I look at the x-intercept. Now here we're just going to have a summary of a comparison between the intervals for fx and f prime x and the second derivative there as well. So let's start off with the original function, right? And I've indicated all those various intervals. Let's just check again. Which one is the d? D associated with the local maximum. And the m, that's right, the m is associated with the inflection point. And let's look at c. C is the x-intercept. So let's look at fx. Now fx, I'm looking now at the yellow, right? We're going to use fx now. And what are the critical values if I look at my graph there? Here, what's going to be critical here would be the, if fx is equal to 0, where's fx equal to 0? By looking at the x-intercepts. Okay, and what are the x-intercepts there? In this case, it is, let's just look at it there. You can see there's the x-intercepts. The x-intercepts are at A, B, and C. And because I have an equal, my answer is x equal to A, x equal to B, and x equal to C. Now we want to see where's fx greater than 0. Fx, so I look at my f graph, where is it greater? What does greater mean? That's correct. Greater means where is it above the x-axis. So I look at where's the graph. You see this portion, there's a graph. This is the above portion of the graph. And where is it above? That's correct. You have to use your intercept. It's between the intercepts there, between A and B. And where is it also? There's another piece that's above, between C and infinity. Okay. Let's look at where is it. Where's the fx below? So I have to look at the below portion now. Let's look at the below. There's the below part. Can you see? This piece and this piece is below. So I only focus on the below. You can actually cover up the top part. Right? If you take a piece of paper, just cover up the top and you can see where's the less than. And here you see there are two less than portions from negative infinity. So less than 0 actually mean below the x-axis. So it's between, come again, between negative infinity and a, and then from b to c. So if you want to find the inequality with fx, use the x-intercepts. Now we're going to look at, let's take that graph away. We're going to look at the first derivative, right? Now first derivative means we have to look at what? We have to look, that's correct, we have to look at the turning points, right? So the turning points, we got it here in this nice blue color, and you can see where the turning points occur. The turning points occur, that's correct, at D, and there's another one at E. So there I've got my two turning points. So if you want to do any inequality or any relationship with the first derivative, you need to use your turning points. So I now have the turning points, and I now focus on the critical values, D and E, and the other points here would be negative infinity and D, and from D to E, and from E to infinity. Now, where is it? That's equal to D and equal to E. But now if I want to find out where the graph is, let's look at this one. I want to see where is it. There's a one greater than 0. What do we mean by first derivative greater? Come, we had it earlier. That's correct. We have to see. You see, there's the greater portion, right? Now, first derivative greater than 0 actually means, where's the graph increasing? There's the increasing part. It increased. There's the increasing, and always work from the left side. From increasing there and then increasing there. Okay, and you can see it increases from negative infinity to D and from E to infinity. You see I've used that symbol there. That's a mathematical symbol that means or. In mathematics we always try to write symbols so we're not restricted to a specific language. There we just use that for or. Right? You can even write in the word or, it will be acceptable. It is correct anyway. Then where's the first derivative less? If greater was increasing, what would less be? Can you picture the decreasing? That's right. Just look, let's see now. There's the decreasing. You see, there's decreasing, and it decreases between the two critical values there, from the maximum to the minimum. So decreasing is between D and E. Now let's look at the second derivative. Let's take that away. Let's look at the second derivative. Second derivative, the critical values you obtain from your inflection point. What is the inflection point? There's only one inflection point. Let's find the inflection point. That's right, at M. So we're only going to use this interval, negative infinity to M and M to infinity, nothing else. So when you work with the second derivative, you only use the inflection point. Where's the inflection point? X equal to M. Now let's look at second derivative greater than 0. There it means that's the second derivative greater than 0. And what did we say that one is? Just follow it. Inflection ends going. That's right. We have to look. Greater than 0 means where is it concave up? And you can see it's concave up on which side of the critical value? In this case on the right side. Not always on the right, depends on the shape of the graph. And that's from M to infinity. The less than means where is it? That's right, concave down. See, there's the concave down. Inflection, don't look at this, it's not going up. It's going up, but it turns. So that is concave down. And it's from negative infinity to M. So that there gives you a nice summary. So when you have the function only, you use the x-intercepts. When it's the first derivative, you use the turning points critical values. And when it's the second derivative, you focus on the inflection point. And there I'm just putting that back again, right? So there you can see which one, this is the down and the other one is the up. Now, here we're going to look at one which is actually a level 4 type of question where we're going to interpret fx times its derivative, right? Or a few other inequalities that we have here. So let's take our function there again. There's our cubic function there. And we've got all the points. You also know what these ones mean. That's the local maximum, local minimum. There's the inflection. Those are the x-intercepts. You do not use y, because we say determine the values of x. So let's look at this here. To be able to understand greater than 0, what does greater than 0 mean? Greater than 0 means positive. Now, what times what gives you a positive number? Come from grade 5 already. Positive times positive, or negative times negative. So I'm going to look at the two options, where the fx is positive and the same time the first derivative must be positive. Positive times positive. Okay, or we can have the other option. We can have negative times negative. So we're going to look at both. Let's look at each one separately. Positive times positive, and then negative times negative. Now let's look at the f positive first. So what does this mean? This means the f must be positive. Where is the graph positive? And the same time, where is it increasing? So let's look at this here. Can you see there's the positive part of the graph? So first try to see where is it positive. There is it. So there you know there it is positive. Now let's look at this positive part of the graph and which part of it is increasing. What is he doing there? Increasing in that part, decreasing in this part. That's correct, increasing. So how many increasing parts do we have? That's correct, right? So if we look at that, and now I've put in, shaded in the increasing. There's increasing and there's increasing. Now we can write the answer down. From, you can see it increases from the x-intercept to the turning point. That's from A to D. Then it's from the x-intercept, which is C, up to infinity there. Right? So this is the one option that we have. Let's look at the other option. When I say that, means where's the graph negative? Where does negative mean? Where's the graph below? See what you can do? You can cover up the top, and let's look at the bottom part of the graph. There's the bottom part. You see, I only have the bottom part of the function, the portion below the x-axis. Now, if we look at the one below, we must now see which part of it decreases. What is this one doing? Increasing, and this one decreasing, and that one increasing. So it increases. If you look at that, you see, so the only place where this decreases, there is only decreasing portion. So that's from B to E, and we can write that down, B to E. Now we can just combine them. See, if you write it down like this and you put a or and that, perfect. Or you can just write it there, from A to D, or B to E, or C. It doesn't matter in which order you put it. I've just placed it in the order as it appears there, you know. First from A to D, then from B to E, and then from C to infinity. But even if you wrote the answer just like that, it will be acceptable. You can also put the word or in between. So please remember, don't look at the one situation. Positive can be positive times positive, or it can be negative times negative. In the previous example, we look at the product where the product was positive. Here we're going to look at where the product is, what does less than 0 mean? Where the product is negative. Now what times what gives me a negative? That's correct. A positive times a negative, or a negative times a positive, right? Let's look at our function again. There we've got the function with all the intercepts and all the critical values. So we're going to look at where the graph is positive. What does positive mean? Look at the portion of the graph that's above, and then looking at that above portion, we'll have to check where is it now decreasing. Then we have the other option. I can look at below the graph, and then looking at the below graph, below the x-axis, I then have to see where is it increasing. Let's do that. This one you have to be very careful when you do that. If positive means above, so let's look at the above portion. There's the above portion. Now of the above portion, which part of it is decreasing? That's increasing, that's decreasing. How many decreasing parts are there? Only one, right? Let's see there. There's it. You see, there's the decreasing part there, right? I've color coded there. There's the decreasing. And where's the decreasing now? From D to B. So I can write down the interval. Let's do the other one. You have to look at below the x-axis again. So I look at below, just don't focus on the above. And of the below, I must see where is it increasing. There it increases, there it decreases, and there it increases there. So let's look at that. And there are two parts where it increases. And if I write that down, and it's the or, you can just write it like that, but you can just bring them together from D to B. That's actually in the middle. That negative comes on this side. But if you put it in a different order, it would be immaterial, right? As long as if you're not sure, just leave it like that. You don't have to combine it that way. And that was the question that we look at, the product less than 0. Now we're going to look at actually some problems that will utilize all these inequalities and interpretations. Let's look at the first problem here. Let's say we are given a function f, so there's the function f, it's the sketch is given with intercepts, and they tell us there's the intercept. Just make sure when you read that, -1 and 0, 4 and 0, always double check whether everything is there, 7 and 0, 0. So if it's not there, you insert it. 1 and 36 are turned, there's 1 and 36, and normally it's advisable to actually highlight the given information. There's even an inflection point. So maybe this could have been done, you had maybe a question prior to this, you sketched it, and all those points were already calculated. Then usually a question would have now questions based on the graph, right? So you have to read it from the graph. Determine the values of x, so the values mean can be more or 1. If it's an equal sign, it will only be 1, right? But if it's an inequality, it's normally an interval. So this must be in interval form, interval form, interval form. Fx less than 0. There we have the given information. Let's look at the first question, fx less than 0. So which points should we require here? That's correct, the x-intercepts. And what are the x-intercepts? Let's look for them. -1, 4, and 7. Okay. Now what does fx less than 0 mean? How do we interpret that? What must we look for? That's correct. We must look at the value below the x-axis. Which part of the function is below the x-axis? Which part of the curve is below the x-axis? And can you see the portion below? That's correct. There's the portion below. So we just have to write it now in interval notation. We just focus on the x-intercepts. So in this case, it is from -infinity to -1, and the other one is from 4 to 7. So we've only been using the x-intercepts there. Let's look at the second part. Let's have the graph back again. F is decreasing. That's quite straightforward. Where's the curve decreasing? Let's follow this one. What's it doing here? Increase and decrease and so which points do we need here for decreasing? That's the turning points. So that is, we're going to focus on the critical values there, which we obtained from the turning points. And that's the decreasing portion as we mentioned earlier. So now we just have to write it in the correct notation from 1 to 5, 7. Or you could even say x between 1 and 5, 7. But this one is much simpler and easier to use. I can recommend that you use the interpolation. Let's look at the third question. F is concave down. So which point do we associate with concavity? That's correct, the inflection point. So where's the inflection point? You see it? That's correct, at x equal to 3, 3. Right? Now, which one is this? This one is let's follow it. And which one? This one is up, and this one is down. So on which side of the inflection point must we work? On the left side. So let's see. There's the inflection point. It goes there, it turns, and it goes down. So where's it down? On the left side. Don't write down left side. We just write it in interval notation. You see, that tells you start there, end there. That's easy. See where you start and see where you end. Let's look at a second example now. There we have the information. Again, read. See, it's the same graph, but we're just going to have different questions on it. right? Same points, just different. We want to see how do we answer these questions here. There's the graph. Let's look at the first one. You see there this is written in function notation. First derivative greater than naught. What does that mean? First derivative greater than naught. Which points do we associate with the first derivative? That's correct, the turning points, right? Can you see the turning points? And what does first derivative greater than naught also mean? Where's the graph? Increasing. So we need to focus on the turning point, the critical values we get there. And now we're going to see where is it increasing. Can you see the increasing portion? Let's try to find it. And there's the increasing. Can you see that increase and that increase? That portion that we left out is the decreasing. Now we just have to write that in. See, it's quite easy if you do it this way. Work from the left, which is from negative infinity to 1. And then the other portion is 5,77 up to infinity. We always have open intervals here. Let's look at the second problem. That's the same graph. What does this mean? See, there's no words here. It's written in mathematical notation. Second derivative we associate with, that's correct, the inflection point. And what's the inflection point? Critical value there is x equal to 3,3. Right? Now, what does second derivative greater than 0 mean? That's correct. Where's the curve? Concave up. And you see the up portion? Is it the one on the left side or on the one on the right side? This one or that one? Sound like an optician now. So there's the up. You can see there from the inflection turn and it's going up. And this is on the right side. The right side I need positive infinity. So it's from 3,3 to positive infinity. Let's look at the third question. Yeah, this is one like we had earlier. And here we have a specific example where we have a product. This product, what does this mean? The product is positive. So we have, for the f, we're going to use the x-intercepts. And for the first derivative, we're going to focus. So there we have the x-intercepts are -1, 4, and 7. And then the turning points are at 1 and 5,7. But positive, we have two options. So if I say the f graph must be above, then the same time I must see where it increases. Now look at the other option. Opposite of that would be below and decreasing. Let's look at, and there we have it. Can you see there? This portion is above and it's increasing. This portion is above and it's increasing. This portion is below and it's decreasing. So there's three intervals. So there's quite, you see, try to sort out that, and you can see it's above and you can just focus on the above. There's the above, and that was the increasing part of the above, which is that portion here. There's the below, and that is the decreasing part. And then we can just read off the intervals from there. Okay, there's it from -1 to 1, and this is from 4 to 5,7, and that's from 7 up to infinity. Let's look at the third problem here. We're taking the same graph, but we just have different questions on it. The point of inflection of G, but this was the F graph. What do they say is G? So let's look at questions here. The point of inflection. So I need to, there's my point of inflection, but this is the point of inflection of F at x equal to 3,3. But now they have a new function defined by gx equal to negative fx. What does negative fx mean? That's correct. That means the graph is reflected in the, so that's the original inflection point, but we want to get the reflection in the x-axis, right? So reflection in the x-axis means that one will stay a 1, but that 36 become a -36, right? And that 5,7 stays. It's the y values that change. So if I reflect that in the, so the x value is going to remain the same. It's the y value that when you reflect in the x-axis, the x coordinate remains the same. So we just change the 10,6 to negative 10,6. Let's look at the second question in this problem. There's the graph. Let's look at the question. The values of x for which h will be concave down, and there h is defined this way. What does f negative x mean? That's correct. It means where the graph must, the f curve must be reflected in the y-axis. Okay, concave down. The original one is concave down. There's it concave down from negative infinity to 3,3. But h is the reflection in the y-axis. It's just reflected in the y-axis. So in other words, this point will go this way, that one will go that way. So let's just see. This is what the reflection looks like. And now can you see where's the concave down now? Concave down. You see there concave down was on the left side. Here concave down is on the right side. So it's from this point, and that point is from negative 3,3. See, from negative 3,3 up to infinity. Let's look at the third question in this problem. Determine the turning points of k, and their kx is defined as kx equal to fx plus 1. Okay? Let's see what we mean by that. Turning points. What are the turning points of f? Those are the turning points. We can read it off from our graph. But now, x plus 1, what does that mean? When you have x plus 1, that's correct. The graph is shifted 1 unit. Plus 1 means 1 unit to the left there. If it's negative, subtract 1, it means to the right. But positive 1 is 1 unit to the left. So I must take 1 unit to the left. So which coordinate is going to change? That's correct, the x coordinate there. So it's 1 subtract 1, which gives me 0. The other one there is 5,7 subtract 1. That gives me 4,7. So these 0 and 36 and 4,7 and negative 14,8, those are the turning points of the new function. Let's look at the fourth problem now. If g is a cubic function, so they have a cubic function, it's not drawn. Gx, so all these, this is all the information that's given, and now they want us to draw this on a grid. So we're going to try to interpret that. So you must, there's no equation given. There are some statements here. G3 equal to G prime 3 equal to G double prime 3 equal to 0. Let's use the given information. G3 equal to 0. What does that mean? X is equal to 3 and Y equal to 0. That is an x-intercept at 3, 0. Let's plot that point in the meantime, and there we have the point there. Let's look at the other given information. First derivative, substituting 3 equal to 0. So there we have x is equal to 3, but first derivative means there that I have a turning, also I have a critical value at 3. So there's a critical value here. Then we have the second derivative, 3 equal to 0. Second derivative, that means that I have an inflection, right? So we have an inflection point at x equal to 3. So this is actually not a maximum or a minimum, it's actually an inflection. G0 equal to 27. That means x is 0, y is 27. That is a y-intercept. Let's plot the y-intercept, and there we have the y-intercept. Then we have second derivative, x greater than 0, but x must be less than 3. So on the left side of 3, what does this mean? Second derivative greater than 0. That's correct. That means I have concavity. So it's concave up. So on this side it will be concave up. And which way is concave up? Let's see. There is concave up. Then we take second derivative less than 0. Second derivative less than 0. That implies I've got concave down. So let's see concave down, and there we have concave down. And there we have our function. Let's look at problem number 5. Here we have the following given information. We have a graph of a first derivative, quadratic there, and there's the graph of the first derivative, right? And then we have some questions based on this graph of the first derivative. Let's look at each of the sub-questions now. There's the graph of the first derivative as given. Determine the values of x for which the graph of g will be strictly increasing. Is this the graph of g? No, this is the graph of the first derivative. But the graph of g decreases if the first derivative is less than 0. So where's the first derivative here less than 0? So that's what we need to do. First derivative less than 0. It's below the x-axis. You see below the x-axis, there's the first derivative. And that is between -4 and 2. Let's look at the second question. We must find the x-coordinate of the local minimum point. Now, local minimum would be where the gradient changes from negative to positive. So let's see now. There the gradient is positive and then negative. So this is not a local minimum. Here the gradient is negative and then it becomes positive. So this is where we'll get a local minimum, right? Changes from negative to positive. There's negative and then positive. Therefore, we have a local minimum at x equal to 2. Let's look at the next one. We want to find the x-coordinate of the inflection point, right? The inflection point of g would be the second derivative, right? But now we have the first derivative there. So the inflection point, if the first derivative is a quadratic, the inflection point would be between those two x-intercepts there. So between them, exactly in the middle. How do we find that? We add the two, -4 plus 2, then we divide it by 2, and that gives us -1. Or, if this is the first derivative that's given, for inflection point, you just find the second derivative. So let's differentiate that. That gives us 2x plus 2 equated to 0, solve for x, and we get exactly the same answer there. You can either find the inflection, which is the midpoint between the two x-intercepts, or you can actually calculate the second derivative and equate it to 0. Let's look at the following question. We must find the gradient of the tangent. Gradient of the tangent is the first derivative. So actually we can use the first derivative. So the first derivative is actually the graph where x is 0. So if I make x as 0 here, I end up with -8. Or I can actually look there. If there's 0, I can actually read it also. There's x0 and it corresponds with -8. So the gradient here, in this case, m is equal to -8. Before you actually start with your exercise, I recommend that you go through some of the worked out problems that we've done in this video. Take the question, try to answer it on your own. After you've done that, then you compare your answers to the solution that was given. And once you've done all of them, then you should be ready to do the exercise worksheet here. And these questions are all adapted from external DBE question papers there. So there we have a given information, and they ask you to work out the values of B, C, and D. You see the B, C, 3 unknowns. So they need to give me 3, and there we got 3 points there already, right? Then they want the coordinates of B. What is B? The coordinates of the turning point. We want the equation of a tangent. Then we must sketch what must we sketch here? We must sketch the second derivative, and the second derivative of a cubic is, can you still remember that? That's correct, it's a linear function. And here we want to know, where is it concave? Up. And we have the similar type of situation here. There's some given information and some questions there. There we even have one similar to what we did earlier. And then there are some more questions. There we've got 2 turning points. You can see what we need to do there. There's another one, and we have different questions based on that. There the equation is given, the graph is sketched, and there are some questions. Then you have to do some interpretation as well. Same applies to question number 5. Here we have average gradient, that average gradient. Some of the work we did in part 2. Here it's just a different form, and here they also want you to sketch the graph. Question number 7, there the first derivative is given, something similar to the last question. Let's look at this question here. This is the last question, question 8. It's adapted from the June 2015 paper. Here we have the graph of a first derivative. There's the first derivative, and we tell you the first derivative at 1 and the first derivative at 3, they are both equal to 0, and we also have the first derivative at 0 equal to 6. So you have to interpret that, right? And then we have questions similar to what we asked from this first derivative graph. You can read off the stationary points, see where it is decreasing, explain why that is a local minimum or a maximum, find the x-coordinate of the inflection, etc. Right? So this is a similar question to what we did previously, and that's the last question. All of these questions here are adapted versions of questions from TBE external papers, like this one here, June 2015. But I've slightly adapted some of the questions, and maybe I've even added one or two additional questions as well. Right? There's only one more part we need to do, and that will be part 5 of calculus, and that should be the end of the series on calculus. Thank you very much.